Hello, am I audible?
Yeah, I think
Hello.
we can hear you, but we cannot
Okay,
see
okay.
your
Yeah,
PPT
let me share
slide
the
at all.
slides.
Okay,
Is the slides visible?
I can see your slide now. Can you put it? Okay, I think it's good now.
Okay, okay, fine. Okay. Let me get the pointer. Okay, okay. Let me then, with your permission, may I start?
Yep. Please go ahead.
Okay, okay, okay. Thank you very much. So, first of all, thank you very much for allowing me or giving me the opportunity to present my research work in such a nice conference. And unfortunately, I was not be able to present physically, but nevertheless, it was also good to kind of listen to your talks and all these things. Okay, so to start with, as you can see, rather a big title, Evidence of Spin Liquid Behavior in the Extended Quantum Critical Regime of Pressurized Cerium, Palladium, Aluminium. So in the title itself, you can see that there are these two terms that has to be kind of addressed before for the sake of completeness, because I know that there are several kind of most of you are kind of aware of the ideas of spin liquid or quantum criticality. Okay, but for the sake of completeness, I would like to say a few words on that. To start with, let me start with the idea of quantum criticality. So before going to the idea of quantum criticality, let me first discuss about the idea of classical criticality. So what happens in case of a classical magnetic second order phase transitions? Okay. So of course, I'm not going to go to this sort of second order phase transitions because I'm not interested in that for the time being, of course. But of course, I am going to talk about for a system on a serious note where there is a classical second order magnetic phase transitions. So as you know that for a classical second order magnetic phase transitions at higher temperature, you have thermal fluctuations that are dominating over the exchange interactions between the electrons. But below a certain classical critical point, the system ordered to a particularly magnetically ordered state where the exchange interaction between the electrons is actually winning over the thermal fluctuations, right? And just above the classical critical point, you see some sort of critical regime. Okay, so in that regime, you would expect that all the physical parameters, as for example, specific heat, susceptibility, relaxation rate, in evaluated from NMR or MUSR, that all diverges towards the ordering temperature. Okay, and all the kind of diverging properties, so they follow some sort of power law behavior. And we know that these are several power law behaviors, and we also know that there are also several universality classes. Depending on the different universality classes, you would expect different sort of power laws. Okay, so these are the things that is rather well established. Theoretically, it has been proposed. Not only that, experimentally, there are several examples of such kind of second order magnetic phase transitions where you see critical behavior just above the critical temperature. So now let us little bit start discussing about quantum phase transitions. So in analogy to the classical phase transition, in case of quantum phase transition, suppose you have a, tuning parameter, as for example, um, pressure or magnetic field, of course, non-thermal tuning parameter. So if you have a system that has a long range magnetic ordering at a finite temperature, if by the application of the tuning parameter, if you are able to suppress down the ordering at t equal to 0, that point is called as the quantum critical point. And around the quantum critical point, you would expect strong quantum fluctuations. And if you increase further, then you would expect some Fermi-liquid behavior and the suppression of the quantum fluctuations. Okay, so just to tell you that what is the sort of interesting behavior that one may expect in the region around the quantum critical point. So we all know that for any sort of phase transition, at the phase transition temperature, your spatial as well as temporal correlation length diverges, right? So Now, the thing is that if we consider that the energy associated with the temporal order parameter fluctuations is h over tau, and this tau is nothing but the spatial correlation time. So we know that for the classical case, where there is a classical second order phase transition, second order magnetic phase transition, we know that the ordering temperature is finite, that is non-zero, of course. And as I just mentioned, that the tau that diverges to infinity. So we know that for a classical case, the energy of the temporal order parameter fluctuations are much more less than that of the thermal fluctuations. So in case of a classical magnetic phase transition, we can of course neglect the impact of these temporal order parameter fluctuations or temporal correlation length. Okay, but on the contrary, in case of a quantum phase transition, we know that the ordering is at 0 Kelvin, right? So here it is just the opposite, that the energy for the temporal order parameter fluctuations are higher than that of the thermal fluctuations. So that sort of incorporation of the effect of the temporal order parameter fluctuations dictates the dynamics of the system. And you get different sort of universality classes compared to the classical second order magnetic phase transitions. And as a result, definitely in case of quantum critical points also, you would expect that all the physical parameter would be diverging towards t equal to 0. But still, as I just mentioned, that because of the effect of further temporal correlation length divergences, the critical exponents are rather less explored, or those are not that much known compared to the classical magnetic phase transitions. So these are one of the important points for dealing with, or this is the reason for which people have been discussing about quantum criticality quite a while. And not only that, on that point, because of the presence of these critical fluctuations, you would expect some non-Fermi-liquid behavior. Okay, and of course, not only this, but also people have seen that there are some situations, there are some systems where the tuning, because of the tuning, before reaching to the quantum critical point, some system shows superconducting behavior as well. And of course, those superconductors are mostly, or I would say all of them are sort of unconventional superconductors because of the proximity to the magnetically ordered state. Okay, so these are the important ideas or important aspects of studying quantum criticality. Okay, so now the thing is that we now understand what is sort of quantum criticality is. So now the question is that by what are the things, or what are the ingredients to like really see a quantum criticality in a particular system. So as I told that then there must be some competing interactions that has to be present in the system in order to achieve this quantum criticality. Okay, so we will be discussing mostly about the systems that are kind of dealing with 4F-based heavy fermionic system. So in this sort of systems, what happens is that at rather low temperature, the 4F moments kind of couples with the conduction electrons, and not only that, but they'll sort of form a single type of state, many body singlet type of states. And as a result, what happens is that the conduction electrons quenches the moment of the 4F moments. Okay, and as a result, you can see that at a further lower temperature, there is no long range magnetic ordering, but the system is kind of showing some Fermi-liquid type of heavy fermionic state. Okay, so this is nothing but the Kondo interaction, and you can easily imagine now that because of the quenching of the 4F moments, you would expect that in that case, dominating the Kondo interaction is you have a lesser chance of having some long range magnetically orders. Right. So, and along with the same, at the same time, we have also other kind of interaction that is called RKKY type of interaction, where the both of the 4F moments interact via this interaction. Okay, and that actually promotes long range magnetically ordered state. So now we see that if this 4F based heavy fermionic system, they have these two interactions, both are sort of competing with respect to each other. So thus there is a finite chance, then you can end up with a quantum critical point if you sort of tune these two type of interactions. And indeed, it was a kind of quite well-known phase diagram proposed by Doniak. So here along the x-axis, this is nothing but the exchange. It can be the RKKY type of exchange. It can be the Kondo type of exchange. And along the y-axis, you have the temperature scale. So you see that while the J is rather small, the Kondo temperature that follows, that is actually, I mean, the Kondo temperature is subdominant, or that is not been able to dominate over the RKKY interactions. So as a result, when the J is rather small, you would expect there would be a long-range magnetic order. On the contrary, if you increase the J values, then you see that the Kondo temperature or the Kondo energy scale is increasing or is dominating over the RKKY type of exchange interaction. And as a result, you can expect that there would be a reduction of the long-range magnetically ordered state, and you may expect some sort of quantum criticality. Okay, so the point is that then it is really interesting to deal with this 4F-based systems, because you have the chance of getting this quantum criticality. Okay, so now let me kind of discuss another way by which you can suppress down the ordering. Okay, that is nothing but it is called as frustration. So why it is called as frustration? So so you can consider that, let's suppose that there is one triangle, and each corner of the triangle there are Ising spins. Okay, so Ising, by Ising I mean is that the spin can be either up or down in the direction. Okay, and if you consider that there is a antiferromagnetic type of exchange interaction between the spins, then you see that the first spin and the second spin, they are aligned antiparallelly. Fine, no problem. But the third spin, it is not possible for the third spin to orient itself in a particular direction. So thus the third spin is sort of frustrated. Okay, and this leads to huge degeneracy of the ground state. So you can kind of construct different type of spin structure, and in all the spin structure, you have the same energy. Okay, and that leads to actually a different states of matter, and that is nothing but spin liquid state, where the spins are highly correlated with respect to each other, but there is no sort of spontaneous symmetry breaking down to theoretically down to t equal to 0, and the spins are rather dynamic in nature. Okay, so of course this is also an exotic state of matter. So now we see that these are the several interactions that can be incorporated in a system. So what is then is going to happen? So my point is that suppose you are dealing with a metallic system, 4F-based metallic systems, and not only that, but also the 4F moments are actually nicely arranged in a frustrated lattice. Okay, so like frustrated systems are mainly been discussed in insulators, but it is also very much interesting, as you can see, that if you have a frustrated lattice where the atomic the magnetic moments are arranged in a frustrated lattice, so the effect of frustration will be there. Not only that, the effect of Kondo interaction will be there, and also on the top RKKY type of interaction will be there. So things are of course much more rather complicated. Okay, so now the question is that if you have this sort of situations, then and you have the kind of this sort of different interactions are present, then would you expect that the phase diagram that I have shown, the genetic phase diagram for quantum criticality, would remain the same? So, so that was actually the question with which we have started kind of discussing or thinking about this sort of problems. Okay, so now the thing is that theoretically it was been proposed by the group of Professor Kumio C. So they kind of proposed this sort of interesting phase diagram. So along the y-axis you have quantum fluctuations, which means that along the y-axis, if you kind of go along the y-axis on the top, more the frustration, you are kind of having more quantum fluctuations. Or reduced dimensionality can also sort of incorporate more quantum fluctuations. And along the y-axis, along the x-axis, you have the Kondo interactions, but in the unit of RKKY type of interactions. Okay, so now you see that there are different type of phases, not only phases, but different type of quantum criticality has been proposed, okay, by them, and that includes spin liquid state. So as I told, that was actually our intention, that if we start with a system, Fourier-based systems where the moments are arranged in a sort of frustrated lattice, and then what is going to happen? And if the system can be is tunable, if the system is tunable, because at the end of the day, we are like looking for the quantum criticality, right? So that was actually our intention, and we were looking for some systems which can be a good candidate material for looking this sort of issues. And we have found out that this particular system, cerium, palladium, and aluminum, that was there for a while. And if you see the structure of the system, you see that the cerium moments are arranged in a Kagome type of lattice. You can see that this Kagome is nothing but sort of cornered shared triangles. It is highly frustrated lattice, but of course the Kagome structure for this particular material is not perfect Kagome, but of course some sort of distorted Kagome. But still it has some frustrated magnetic structure and frustrated arrangement of the cerium moments. Okay, of course this system is metallic, and the other thing that we want is that the system must be tunable. And we have checked and we have found out that, of course, if you apply pressure, you can see in the middle, you can suppress down the ordering, maybe around 1.1 GPa. Not only that, but the chemical pressure also suppress down the ordering. Even magnetic field also suppress down the ordering, going through different type of magnetically ordered states. Okay, you can see that the parent compound, without the application of magnetic field or pressure, it shows some ordering around 2.7 Kelvin. Okay, some long range magnetic ordering. But so that is why we have chosen this system. It has the tunable, so it is highly tunable by different means. Not only that, the cerium moments are arranged in a nicer Kagome type of frustrated lattice. Okay, so that's why we choose this particular system in order to address the problem that we have mentioned. Okay, so before going to this particular system, let me tell you one more thing, is that in a normal insulating system where you do not have any Kondo or RKKY type of interactions, there, the definition of degree of frustration is defined by this parameter, as you can see. So it is nothing but the ratio of the Curie theta over the ordering temperature. Okay, so so usually in a normal unfrustrated system, you would expect that these are almost would be similar in magnitude. Okay, but in case of frustrated system, the exchange interaction is much more, but the system is unable to go to a long range magnetically ordered state because of the effect of the frustration. The ordered state comes at further lower temperature. So more the difference between the Curie-wise theta with respect to the ordering temperature, you have more degree of frustration. Fine. So that is that particular description or that particular definition was rather very much well celebrated in terms of in the case of insulators. But you know, as I told, that we are dealing with in metallic system, because in metallic system at higher temperature you have this Kondo, you have this RKKY, there are others, all these sort of interactions are there. So there you cannot sort of use the same definition of frustration. Okay, so one of the paper mentioned in this kind of defined by Oliver and co-workers from Max Planck Dresden. So this is actually the data for cerium, palladium, aluminum at ambient pressure, susceptibility versus temperature curve. So if you just consider the data that I have like denoted by this dashed red one, that the data has been taken at the field of 0.01 Tesla. So you can see that there is a hump at around T Ts defined by Ts, the hump, the temperature at which the susceptibility is showing the hump, and Tn is defined by this point. Okay, so now what they kind of have seen is that Ts is actually the point at which they have seen that there is a high entropy accumulation above the long range ordering. And we also know from our basic understanding that in a frustrated system, you would also expect, you are always going to expect that there will be a high entropy accumulation above the ordering temperature because of the presence of frustration. So what they told is that instead of this Curie-wise theta in a metallic system, you can consider that this Ts might be to some extent dictating the fact that where the system would have ordered if there would not have been any frustration. Okay, so that's why they sort of defined the fact that the temperature region between Ts and Tn it is some sort of spin liquid type of behavior, as similar to the example that I have given for the insulator in the left hand side. Okay, so this ratio is actually rather giving you the idea of this frustration, degree of frustration in a metallic system. Okay. Okay, so keeping that in mind, let us proceed further. So, as I told that we are going to discuss about the quantum criticality in this particular system. And in order to know what is the quantum critical fluctuations, you have to employ some technique which has the capability to show dynamical behavior. And muon spin relaxation or rotation technique is one of the important technique in that aspect. Okay, because of the limitation of time, I won't be able to say you a lot of things regarding muon spin relaxation technique or Mayukh technique in short. But quickly, I will be going through one slide that will give you the overall idea that what it actually is. Okay, so just consider that these muons are spin half particles. So as soon as I tell you that muons are spin half, you can easily recognize that it is very sensitive to the local magnetic field. As soon as the muons that are being placed in the interstitial position of the crystal structure, it's if there is a long range magnetic ordering, it sees the local magnetic field produced by the local moments around it. Okay, and as soon as it sees the local moment or local field, it starts to precess. And this precision frequency is nothing but proportional to the order parameter. Okay, so now this is the typical Mayukh data, this asymmetry as a function of time. You see that there is a nice oscillations. The data has been taken below the ordering temperature. So this oscillation, if you take the Fourier transformation of it, it is going to give you the idea about the local magnetic field. Okay, this is nothing but the precision frequency. Okay, so if you track that, you will be able to figure it out, the order parameter. Okay, so now forget about the order state. In the paramagnetic state, you only see relaxation behavior, and this lambda denoted by and that is nothing but 1 over T1. That is actually, as you can see here, is probing the electron spin dynamics in the paramagnetic state. Okay, so this lambda over T, this parameter, is nothing but is proportional to the imaginary part of the dynamical spin susceptibility. So essentially, if you plot lambda over T as a function of temperature in the paramagnetic states towards the ordering temperature, you would expect that it is also going to follow some power law behavior. Okay, so essentially, this is very important in order to understand the data that I am going to show you in the upcoming slides. One more thing is that there is another sort of experiment that can be done by Mayukh, that is called weak transverse field experiment, by which you can get an idea about the long range, about the ordering temperature. Okay, I'm not going to the detail of it. Okay, so now let us little bit discuss about the data on cerium, palladium, aluminum at ambient pressure and at zero field. Okay, so as I told you in the inset, it is clearly shown that in the long range order state, it shows some oscillations, and in order to deconvolute the spectra, we have used certain functions, and that tells you that there is an incommensurate magnetic ordering, and that is consistent with the neutron scattering experiments. Okay, nothing that much important to say. Okay, so let us concentrate on the temperature dependence of lambda over T. As I told you, in principle, it should show some power law behavior towards the ordering temperature. And indeed, it is more or less the showing some power law behavior for this cerium, palladium, aluminum at ambient pressure. Okay. Not only that, but in order to deconvolute the spectra, we have this electronic part, and we have seen that you need to employ some parameter that is called beta, that is well known as a stretched exponential parameter, and that the involvement of beta is only was there just above the ordering temperature. Okay, so there is a characteristic temperature denoted by T star, below which we have seen that the beta values are deviating with respect to 1. Okay, and interestingly, we have seen that the T star, this characteristic temperature, is exactly at the same point, more or less, within the error bar that mimics the temperature scale of the hump in the susceptibility. Okay. Okay, moving forward. So now we will be discussing about the thing, what is happening if you apply pressure. Okay. So we have applied. Yes.
We have 5 minutes left.
Okay. Okay. Yeah, I'll soon wrap up. Okay. So from the weak transverse field measurements, we have carried out the sort of ordering as a function of the long range magnetic ordering as a function of pressure, and we have seen that the critical pressure is of the order of 0.92 gigapascal. Okay. So now moving forward. Maybe I'll skip this. Okay. So now, as I told that we have done experiments, MUSR experiment at different pressures. And these are the data points I have shown you for the systems which has a long range magnetic ordering. As for example, this 0.89 GPa, it is very close to the quantum critical point. You see that there is a ordering at around 350 millikelvin. And you see, of course, there is a critical divergence of the lambda over T. So now the thing is that what is happening beyond the quantum critical point? And with our surprise, what we have seen is that you can see the data taken at 1.62 GPa and 1.18 GPa, where 1.62 GPa is almost 1.75 times than that of the critical quantum critical pressure. Still, we see some divergences of lambda over T. And that actually very much surprising. That actually tells you that you have the critical fluctuations, quantum critical fluctuations that are still surviving much higher than that of the quantum critical point. Okay. And that actually tells us that this is actually the generic phase diagram that I have discussed. And that might be associated with the fact that because of the incorporation of frustration, we have not only a quantum critical point, but we have rather a extended quantum critical phase by the incorporation of the frustration in this particular system. Okay, so we have got the microscopic evidence of having an extended quantum critical phase in this system. And as I told you that this beta, this T star temperature below which the beta starts deviating from 1, that also changes as a function of pressure. Okay, and as I told you, this beta, the T star temperature is nothing but exactly mimicking this TS. Okay, below which you would expect some spin liquid behavior. So what we have so this is actually the full phase diagram. You can see I have plotted this T star from our experiment as a function of pressure. And I have also given the value of these gray squares from other paper that is nothing but the pressure dependence of this TS, where you have the hump. You see that they are quite matching with respect to each other. So indeed, this T star and TS, they are kind of leading to the same energy scales. Okay, and as I told that below the T star TS temperature scale, we have sort of correlation of spin liquid like of correlations. So we have, of course, evidence of an extended critical phase, and not only that, but also it seems that the correlation between the spins are mimicking or kind of the correlation between the spins are to some extent similar to that of a spin liquid. Okay, and in my conclusion, I would like to say that we have got the microscopic evidence, local evidence of this extended quantum critical phase with the pressurized cerium, palladium, aluminum. Not only that, below a characteristic energy scale, we have seen that that is nothing but critical spin liquid. Okay? And thanks for your kind attention, and I am open to accept any questions and comments.
Okay, thank you. Okay, so this talk is open to question. Any question? I have a quick question. So
Yes, please.
one time you showed global quantum phase transition phase diagram. X-axis is J, Y-axis being frustration, right? Where do you put cerium, palladium, aluminum in those global phase diagram?
Okay, let me.
Yeah, I think you should
This is the
no,
thing?
global
Is it the slide you are mentioning?
the global phase diagram. This is just Young model.
Global. Okay. Yeah.
Yeah,
Yeah.
here. Where do you put cerium, palladium, aluminum?
Yes. I would expect that maybe the kind of cerium, palladium is aluminum is around this point
Right, then
where my cursor
what
is. So
happens if
you
you apply
have
pressure?
a long range magnetic order state, yes, and with pressure you are entering to the spin liquid state.
So what happens if you apply pressure? In which direction do you think it will go? Does it go straight upward or?
Yeah, it is rather difficult to say because under pressure, I do not remember. I mean, it might be difficult to figure it out that whether the Kondo interactions or the Kondo temperature is in which direction it is going actually. So that's why I do not know whether the movement would be along the or I would say maybe on a more safer side there will be some angle. It must not be completely straightforward in the upward direction. I would say that maybe with the application of pressure the Kondo is also going to enhance. As a result, you would expect that there will be some angle with respect to the y-axis.
Okay, thank you. Is there any other question? If not, let's thank the speaker and then all other speakers too. Thank you.
Thank you very much. Thank you.
And I think it is